Hello, my name is Paulina Naydenkov, and I did my project on using deep learning and underground cameras to identify and track sea moria larvae in soil. Before I get into how the model is built and how we assess the model for its fidelity, I would like to discuss the background and previous work done in this field. After, I would like to discuss the next steps that my project can take. The Earth's climate keeps ecosystems in balance and provides all the fundamentals necessary for life. In recent years, we have seen the climate changing in unexpected ways. To ensure that our quality of life and survival are not impeded by this change, we need to be able to track the Earth's climate and its effect on ecosystems. We would like to image arthropods relevant to climate change underground. It would be beneficial to have a program that can automatically identify and count the arthropods in soil so we can have real-time data concerning the arthropod population, numbers, and behavior. So a little bit of background. Here we see on the left is a camera built by the Young Laboratory used to monitor rhizosphere activity. It was used to monitor chemical levels in soil and different fauna in the soil, specifically root growth. Here on the right, we see object detection. Object detection is a computer vision technique for locating instances of objects in images or videos. While humans can look at an image or a video and can recognize and locate objects of interest within a matter of moments, computers can't do this right away. The goal of object detection is to replicate this intelligence using a computer. Object detection algorithms typically leverage machine learning or deep learning to produce meaningful results. You can use a variety of techniques to perform object detection. Popular deep learning-based approaches use convolutional neural networks, or CNNs, such as RCNN or YOLO, to automatically learn to detect objects within images. We can choose from two key approaches to get started with object detection using deep learning. We can either create and train a custom object detection, or we can use a pre-trained object detector, like Detectron-2. Many object detection workflows use deep learning to leverage transfer learning, an approach that enables you to start with a pre-trained network and fine-tune it for our applications. This method can provide faster results because the object detectors have already been trained on thousands or even millions of images. So our RCNNs is a two-stage network. First, it identifies a region proposals or subset of images that might contain an object. The second stage classifies the objects within the region proposals. This two-stage network can achieve very accurate object detection results. However, it is typically slower than a one-stage network. This shouldn't be too much of a problem as we have a smaller data set. So now let's get over how the training is actually done. So we have an image and we annotate it with certain points. Then this annotation and image gets fed into our algorithm and it is shown to be, okay, this is an instance, this is an arthropod, this also is an instance and an arthropod. Then the model gets trained on these training images and should be able to predict and see an arthropod from a totally new image. Here we have a testing set which makes the fidelity of the testing evident. Here we have an arthropod that has annotations, but the computer simply sees the image without annotations. Then it will predict where it thinks the arthropods are. It predicts here, which is correct in this case, and we can see if the model has high fidelity when predicting the instances. So the model that we'll be using is Detectron-2. I also mentioned YOLO before, but we are using Detectron-2 because it has been proven to have a higher recall and accuracy than YOLO. The device that we are training on is a GPU. The configuration file path is a 50 FPN. We are using this because it has been proven to work best with smaller data sets. The learning rate that we found to be optimal was 0.0025 with maximum iterations of 1,000. The instances that we trained on are Z. moria larvae, or beetle larvae. We chose this for two reasons. The first is that it's really evident and obvious where it is in the soil, so humans and computers should be able to easily see it. The second is that beetles are widespread throughout the world, so we can use this program across different ecosystems. Before I go into the exact imaging that we did, I would like to discuss how we evaluate the fidelity of our model. This problem is both object detection and image classification. First, we will do an object detection assessment. If an object is detected, it will be treated as an image that has to be classified either as an instance or not an instance. So if we follow the flowchart, the first question, is something detected? If no, then we see if it's marked as an instance. If it is marked as an instance, then it is a false negative, meaning that the computer missed something that was there. If something is detected, we ask, does it pass the confidence threshold, which is simply how sure is the computer that this instance is an arthropod. If it doesn't pass the confidence threshold, then it's as if nothing was detected, and we have to ask again, is it marked as an instance? And if yes, then it's a false negative. If it does pass the confidence threshold, we also ask, is it marked as an instance? If it is, then it's a true positive, and the computer program accurately predicted an instance of an arthropod. If it is not marked as an instance, then it is a false positive, which means the program is detecting something that is not there. The first method we used to image the arthropods is bright field imaging, which is a grayscale imaging technique. We also employed two imaging process techniques to explore the different fidelities of different image processing techniques. The first is a bright field image with no image processing whatsoever. The second is a compilation of two subtracted bright field images that are 10 seconds apart. We chose for the images to be 10 seconds apart because 10 seconds seem to have enough time for the arthropods to move, but a short enough time that we do not lose time-relevant data for the time to be too long in between frames. The third method we used is simply color imaging with no post-processing after. As you can see, the arthropods are quite evident in the soil as well. So let's see the evaluation of all these methods. Let's start with the raw bright field. As you can see, we have a 84% precision, which is simply true positive over true positive plus false positive, and a recall of 83%, which is true positive over true positive plus false negative. The subtracted bright field with a confidence threshold of 0.5, which is the optimal confidence threshold for both bright field imaging techniques, is comparable with a precision of 85% and a recall of 81%. Now let's look at the color images. We see a massive improvement in both precision and recall in this imaging technique, with a precision of 93 and a recall of 94 for a confidence threshold of 0.8 and an 88% precision with confidence score of 0.5 and a recall of 97%, which is above what we would like of 95%. So how could we get a higher precision? Well, it'd be amazing if we could get rid of some of these false positives. So that's just what we're going to do. Let's look at the false positives that we have. We first here have a double count false positive. Where there is an arthropod present, it just gets detected twice. Here we see that this is quite a popular false positive in all of the imaging techniques. Next, we have a false positive where the arthropod is broken up into two with no intersection of the boxes whatsoever. Here we see it's not as popular in the different imaging techniques, but is still present. And the third instance is a true false positive of nothing being detected whatsoever, of nothing being there whatsoever. The difference here is that the color images have minimal amounts of these instances where it thinks nothing is in fact an instance, while the raw bright field has a lot of instances where it will annotate things that are not instances as instances. So if we can get rid of these two boxes, it would make the raw color in both confidence thresholds extremely high in precision and recall. So that's exactly what we're going to do. We're going to eliminate the double positives by taking each frame's predicted boxes and seeing if any of them intersect. If their intersection is higher than or equal to an area of a smaller box, then the smaller box gets deleted. This ensures that only the double counted false positives get deleted and nothing else, including the true positive and the second type of false positive. Only the double counts get deleted because they are necessary to increase the fidelity, but the other ones don't have a very relevant effect on the recall and precision. So we can keep those for now. We delete the smaller box because it will leave a consistent center of box and also consistent length of box. So how much did this eliminating double positive affect our precision? Well, for the 0.8 confidence score, it turned 93 to 98%. And for the 0.5 confidence score, it turned an 88% to a 97%, which means that the color model has a high precision and recall. So now that we have the ability to detect accurately the arthropods, we would like to count the alive ones and also track them throughout frames. It is important to count the alive arthropods because if we look at population studies and the effect of the different stimuli have on the population, then if we simply count how many instances we see, we won't see a change in population if some die. So we will be able to see movement to gauge stimulus response. The method we will use to gauge if an arthropod is alive or not is a distance method. If the center of each detection box is not moving, then we say that it is dead. For example, this arthropod right here has no movement whatsoever, so we would say it is dead. This arthropod right here has a little bit of movement, and it would be iffy if it was dead or not. However, the center of each box would be outside of the radius threshold that it would be considered dead, so it is alive. Then we have this arthropod with a very long movement, so it'd be considered alive. And here we have an arthropod that completely disappears from the frame. It would be considered alive as well because it needed to move to get out of frame. This is important analysis and filtering to do because out of the 160 instances that we see, only 76 of them were actually alive. So now that we can tell the difference between alive and dead, we would want to track the larva across the frames. So here we will also implement a distance approach. We see here the two frames, and we, with our eyes, can say that obviously this is larva 1 and larva 3, but what the computer does is that it sees that this box has a center here, and it engages that center here and says, which box has the closest center to the previous center? And it would be the center of this larva right here. So both will be marked as the same larva, larva 1. Same here with larva 3. It will project the center onto the second frame and see which arthropod center is closer. And in this case, this is closer. So this arthropod will be the same as this arthropod. And in larva 2, the center has no center close to it, so it will be considered as gone, and the tracking of that larva will stop. Some further work can be done in this project. We would like to explore using subtraction of color images to decrease the noise of the soil in the images. It has been proven that subtracting the images does decrease noise. However, we need to optimize it so that the signal of the arthropods is not lost. We could also use this program to track the population of the arthropods to different stimuli. We could, for example, put more CO2 in the soil or different waste products in the soil and see how the arthropod behavior will change or if more will die in result of the different stimuli. We could also explore a different arthropod to train and test on. This model should be applicable to most arthropods as long as it can be imaged on a camera. I would like to acknowledge Omeg Zhang and Changguai Huang for their continuous support and help with the project. Thank you.